right, ladies. So what you're going to be doing for Friday's class is looking at a video on how to do a titration lab. And Flint Scientific has put this together and has made this available with all the distance learning that's going on right now. And it's really a pretty good job. Now, also part of this, you have a lab sheet. You also have a data sheet, all of which can be found in OneNote and on Moodle. And so you need to go ahead, watch the videos that are embedded in this PowerPoint. So on Moodle and in OneNote, not only will you have a link to this screencast, but you will also find this PowerPoint with the videos in it, in which some different instructors or scientists have actually done an acid-base titration. So what you're going to do is just observe a titration, and we're going to go over a couple of little applications, why titrations are done. Look at some error analysis and look at a little acid-base chemistry. So the makers of this set for the distance learning found this article in which Coca-Cola determines how much citric acid is in their product doing an acid-base titration. So realize that there are different kinds of titration. I don't know if y'all remember, but in the beginning of the semester, y'all did a redox titration. So there are different things that you can look for within a titration. Obviously, clearly what we're focusing on right now is acid-base titrations. Yet another article showing you some of the uses of titrations, this one for pharmaceuticals. And if you look over here, you'll see the use of a acid-base titration, and this is to determine the purity of the enzyme products and to investigate the kinetics of the chemical reaction. So how quickly will it happen? All right, so the very first thing you do is we're going to watch the standardization of a sodium hydroxide solution. I'm not going to go and show you the videos that are embedded in this PowerPoint within the screencast. I want you to stop the screencast, go to the PowerPoint, watch the videos that are embedded in there. Once you've watched this video on the standardization, stop it, come back to the screencast, and we'll kind of keep going from there. Now, the sodium hydroxide is going to be what is put into the burette. It's going to be the titrant. Okay, so this very first thing, and if you come here, you'll see you have, at first it looks like just a black box, but if you go down there to that bottom left of the black box, you'll see the little play sign start up. And then this woman here is going to show you how to standardize your titrant. All right, so part of what you have in this is some data. So one page in OneNote, one of the documents on Moodle is just your lab data. And so you're going to want to open that up and go ahead and fill in the actual lab sheet with that data so that you have all that data in one place and you're not constantly flipping back and forth between the two pages. So the first thing you do is you use your equation to calculate the concentration of sodium hydroxide from the standardization data. Now, I do want you to pay attention. Let's see if I can get that pen to work. All right, got it in red. That's fine. Notice that they, oh, okay, try that again. Okay, notice that they are calling it KHP. Oh, I did it again. Okay, that is the short way to write the formula. Ladies, that's not the actual formula for the molecule. Do not use one potassium, one hydrogen, and one phosphorus to figure out the molar mass. Okay, that would be very wrong. The actual formula is written all the way up at the top of the lab sheet. Okay, so you need to go ahead and scroll back up to the top and look at that actual formula for KHP and use that, which it has like potassium, hydrogen, carbon, oxygen in it in order to determine the molar mass of KHP. Now, why am I even talking about the molar mass of KHP when the question is asking to calculate the concentration of sodium hydroxide? Okay, the reason for that is you are going to start this off, besides finding the molar mass of KHP, but the whole reason for that is so that you can do a stoichiometry problem. Okay, so you're going back to Chem 1 material and you are going to go from the mass of that KHP and you're going to do a stoichiometry problem that then takes you to moles of NaOH. Now, why is it important to go to moles of the sodium hydroxide? Well, don't forget, you're looking for concentration. And what's our formula for concentration? Moles over liter. Now, you have your volume information right there. Now, don't forget, you need to convert that mils. Don't forget, you need to convert your mils to liters. Okay, so this step one does have multiple steps in it. Okay, because you need to find the molar mass of KHP. Don't forget, scroll all the way to the top where you can find the actual formula for KHP. Then you're going to set up a stoichiometry problem where that will go from the mass of KHP, which is right here. So mass of KHP to moles of sodium hydroxide, then you're going to take that answer and put it into your molarity formula. And that way you can have the correct concentration of sodium hydroxide. Ladies, don't forget about significant figures. Make sure your answer is in the proper number of sig figs. All right, so then the next thing they're going to do is show you a video of the actual titration of how you can determine the molarity of vinegar, also known as acetic acid. And once again, we don't know the concentration of acetic acid, so this is going to be that chemical, that solution that's in our Erlenmeyer flask underneath the burette. Once again, you're just going to come to the bottom. See if I can change back into to the arrow. And once again, you're just going to come to this bottom left, press play, and you should have a new person. So you have a new woman here who's actually going to perform the actual titration for you. Once again, you see a setup that is just like what I showed you in your notes. You have that ring stand, you have your clamp, you have your burette. There we see the valve on the burette. Our Erlenmeyer flask that contains our acetic acid and our indicator. Oh, let's see if we can't get it to go forward. All right, and then in this video, they're going to do a close-up so you can see just a little bit closer what is actually happening. Get the camera closer up to that Erlenmeyer flask so you can see what's happening in there. Okay, there, oh, there we go. All right, so now you've seen all the videos on how to do a titration, and now Flynn has quite nicely given you your data that you need if you had done the titration yourself. So once again, this data can be found on a separate data sheet, and you need to go ahead and copy that onto your lab sheet so that you have all the information necessary to perform your calculations. So you will see that the second thing you need to do, the second calculation is right here, and we're going to try to determine the concentration of acetic acid. Now, they are doing this a little bit different with a different formula than what I showed you in your titration notes. The reason why the formula that they're using works is because everything is at a 1-to-1 for the stoichiometry, for the coefficients. If it wasn't 1-to-1, we'd probably have to change our formula just a bit. But you can go ahead and use the formula that's given to you right here. M sub A times V sub A equals M sub B times V sub B. And I'm trying to see what else they have here. Oh, here's a question I have for y'all. Notice that you have molarity times volume. Do you think that you need to take those volumes and convert them into liters? Hopefully you answered no, that you realize you don't have to convert these particular milliliters into liters. So my question probably, or what you're probably wondering is, well, why not? And the reason for that is when you manipulate this equation, you're going to end up with V sub B, or MB times VB over VA. So the milliliters in the numerator are going to cancel out the milliliters in the denominator, leaving you with just those units for molarity, for concentration. So you are going to perform that calculation twice. Okay, so don't forget you need to perform that calculation twice. Hopefully it'll, nope, it didn't. Let's try that again. All right, so you're going to do this calculation twice. Once for trial 1, and then you will do it again, that same formula, for trial 2. Then after you do that, don't forget, ladies, to determine what is the average concentration. Okay, taking your final answer from trial 1, taking your final answer from trial 2, and using that to figure out what is the average of those two. Okay. All right, these are the last two questions that you have on that lab sheet. For question 3, because we're not actually doing this lab, because we don't have bottles of acetic acid in the classroom, just go ahead. Oh, I did it again. All right, go ahead and just skip question 3. But I do want you to go ahead and do question 4. This is a really interesting question and gets you thinking about error, sources of error, and also trying to avoid that error before it ever happens. So the question is, what was the purpose of rinsing the burette with sodium hydroxide before beginning the experiment? How could not doing this affect the calculated unknown concentration. So another way to kind of word this or to look at it is, what if you had rinsed the burette with water before putting the sodium hydroxide in there and starting your titration? What do you think might have happened to our what we would have calculated as our concentration of acetic acid? Do you think that concentration would have increased? Do you think that concentration would have decreased? Okay, so think about it in regards to that instead of having used sodium hydroxide, you decided to rinse the burette with just pure water. And I think that's it on questions that you need to answer. But they do have a couple of more things in the slideshow that I'd love for you to take some time and look at. One of them being a titration curve, a titration graph. And this is for the acetic acid with the added sodium hydroxide. So this would be a weak acid, strong base titration curve. They have the equivalence point, it looks like, at pH of 7. I kind of questioned that a little bit. I'm wondering if that equivalence point shouldn't be a little bit higher, and that this line would have started up a little bit higher as well, because that seems like a very strong acetic acid for it to be at a pH of 1. But anyway, hopefully you understand what you're looking at now after doing the reading from Khan Academy. You understand what you're looking at, that obviously what we started with in the Erlenmeyer flask was an acid. How do we know this? Because we're starting off with 0 sodium hydroxide in the flask in a very low pH. That low pH means that there's only hydronium ions present. And as we keep adding sodium hydroxide, we see that the pH increase until we hit 20 mils, or right around 20 mils, which this makes sense. If you go back to your data, you will see that the amount of sodium hydroxide added was just a little bit less than 20 in one trial and just a little bit more than 20 in the other trial. So it makes sense that we see our equivalence point happening at the 20 mil mark for the sodium hydroxide. All right, and here is just one more video showing you yet another application of acid-base chemistry, and this is on all the antacids that are out there, whether that's milk of magnesia, Tums, Alka-Seltzer, you name it. There's definitely lots of antacids on the market nowadays. Everybody seems to have an upset stomach. And that's once again some really good acid-base chemistry. All right, and that's the end of a slideshow. So hopefully now you have the information and the understanding necessary to do this at-home titration lab. And then don't forget, once you have it done, to submit it to Moodle.